Welcome to Math TV with Professor V. This video is on section 2.5 linear equations in our differential equations video lecture series. Definition: a differential equation of the following form, a1 of x times dy dx plus a sub 0 of x times y equals g of x is said to be a linear equation. The standard form of a linear differential equation is the following: dy dx plus p of x times y equals f of x. Let's break this down first. Notice this is said to be a linear equation because y and its derivatives are all raised to the first power. The coefficients are functions of x only. All right, and then when we go ahead and solve a linear differential equation, we need to put it into the standard form, which is here. So you want to be able to isolate the derivative dy dx and the variable y, which should only be raised to the first power, times some function of x, and then that's equal to another function of x. There should be no other y's in the equation running around, okay? So here's the steps. Hopefully some of them are familiar and you remember learning this in Calc 2. If not, listen up. Step 1, rewrite the equation in standard form if it isn't already. Second, you need to find the integrating factor. The integrating factor is mu of x, which is equal to e raised to the integral of p of x dx. Why this is, most textbooks should give you a nice little breakdown if you want to read through the proof. Step 3, multiply both sides of the equation in standard form by that integrating factor. So you're going to multiply mu of x on both sides of the equation. Rewrite the left-hand side of the equation as follows. It should be the derivative with respect to x of mu of x times y. That's what the left-hand side should be. Remember, e raised to the integral of p of x dx, that's mu of x. And then that should equal mu of x times f of x. You always want to check that that's true. So when you rewrite your differential equation after multiplying both sides by the integrating factor, the left-hand side should be the derivative with respect to x of mu of x times y, and that equals mu of x times your f of x. From there, you're going to integrate both sides of the equation and solve for y. All right, let's work through a few examples. Example 1 says, find the general solution of the given differential equation. State an interval on which the general solution is defined. All right, so first example here, we have 1 plus x squared dy plus xy plus x squared plus x dx equals 0. Now, I know we're focusing on linear differential equations, but I want to review briefly all of the differential equations that we've studied so far and how we know that this differential equation does not fall into any of those categories, okay? So the first kind of differential equations that we studied were separable. So is this differential equation separable? Well, let's isolate dy dx and see. So we have 1 plus x squared dy equals negative xy plus x squared plus x dx. And then if I divide both sides by 1 plus x squared and dx, then I get dy dx is equal to negative xy minus x squared minus x over 1 plus x squared. So I can clearly see this is not going to be separable. Look at that. So that technique or that method of solution would not work for this differential equation. All right. What else did we learn after that? Oh, we learned about exact equations, right? So let's check, is this exact? Do you remember the criteria? I'll remind you right now, don't worry. So remember, whatever function is multiplied by the differential dy, we call that n of xy, and whatever is multiplied by dx, we call that m of xy. And when we want to check whether or not a differential equation is exact, we need to check if del m del y is equal to del m del x, right? So del m del y, take the partial derivative of xy plus x squared plus x with respect to y, you just get x. All right, now let's check what is del n del x. So take the partial derivative of 1 plus x squared with respect to x. Derivative of 1 is 0. Derivative of x squared is 2x. Are these equal to each other? Why, no, they are not. So this differential equation is not exact. All right, so let's see. Is it linear? You probably guessed that it is since I'm doing the example now. But at the end of your differential equations course, or when you take an exam, they won't identify the differential equation for you in most circumstances. So you're going to have to do this mentally or off to the side when solving. So last criteria to check is if it's linear. Is this linear? Let's see. Let me rewrite the original down here. So we've got 1 plus x squared dy dx plus xy plus x squared plus x equals 0. So can I rewrite it in the form that a linear differential equation should be in? So let's see here. We've got 1 plus x squared times dy dx plus xy, and then let me move over the terms that involve x only to the other side. And notice, yes, do you remember the original form that I wrote a linear equation can be written in? We have a sub 1 of x dy dx plus a sub 0 of x times y equals some g of x. And yes, I see it. That's my a sub 1 of x. That's my a sub 0 of x. And over here on the right side, that's g of x. So yes, indeed, this is a linear differential equation. Hooray. Now that we've identified it, let's solve it. So this form is not useful for solving. We want to write it in the standard form of a linear differential equation. So here, let's start the solution process. First, standard form. This you need to burn in your brain, okay? dy dx plus p of x times y is equal to some function of x. All right, so let's isolate dy dx. In order to do that right here, I'm just going to divide everything by 1 plus x squared. Can you see that? All right, good. So we've got dy dx plus x over 1 plus x squared times y. I like to write that little y a little off to the side so I can clearly identify what the p of x is, right? You see what I'm doing? And then that equals negative x squared minus x over 1 plus x squared. So now notice, all right, p of x is right here, x over 1 plus x squared. And then f of x is here on the right-hand side, negative x squared minus x over 1 plus x squared. Lovely. Now it's time to go find our integrating factor. So step 2, mu of x is equal to e raised to the integral of p of x dx. So we've got here e raised to the integral of x over 1 plus x squared dx. Now I'm not joking. At this point in your calculus career, you should be able to just do this antiderivative in your head, all right? If you can't, how would you do it? Well, what are you thinking of mentally? You're letting u equal 1 plus x squared. Then du is 2x dx, so 1/2 du is x dx. And then you basically end up with e raised to the integral of 1/2 du over u. All right. That should be something you can compute in your head. If not, work towards it, or just practice more integrals until that one's not a big deal for you. So we're going to end up with e raised to the 1/2 times the natural log of the absolute value of u. U was 1 plus x squared. I don't need a plus c. This integrating factor is just going to be a function that enables me to integrate my differential equation. So the constant is irrelevant. It's not going to play a part in the final solution, right? This function is just a tool. Can we clean it up? Well, let's see. Yes, of course. I know my properties of logarithms. This 1/2 becomes the exponent here on the argument, right? And then 1 plus x squared, that's always positive. So I don't even need absolute value there. No. So I have e raised to the natural log of the square root of 1 plus x squared. And that's just going to simplify to square root of 1 plus x squared. So there's my integrating factor. All right, now that we've got our integrating factor, step 3, I'm going to multiply my entire equation by it. So there's my original differential equation up here in standard form. Multiply everything by that mu of x. Okay, here we go. So we've got square root 1 plus x squared times dy dx plus square root 1 plus x squared times x over 1 plus x squared times y. Oop, there's my squared. Equals negative x squared minus x over 1 plus x squared times the square root of 1 plus x squared. All right, let's clean this up just a wee bit. The first term stays the same, rad 1 plus x squared dy dx. Notice I can cancel out this rad 1 plus x squared, and then now I have a rad 1 plus x squared in the denominator there. So x over rad 1 plus x squared times y. And then this equals, notice on the right-hand side, I can do the same thing, right? Cancel out that, ooh, that was aggressive. Cancel out that rad 1 plus x squared. And then now this 1 plus x squared in the denominator becomes rad 1 plus x squared. So we have negative x squared minus x over rad 1 plus x squared. Okay, step 4. This is important. Don't be lazy and skip it. You need to confirm that the left-hand side is indeed the derivative of mu of x times y. Okay, the integrating factor times y. This is something you need to check. And it's important to do so. It should always work out, right? As long as you follow the steps properly. But check, because you can catch a lot of silly mistakes that you make if this doesn't hold out. So I want to make sure that the left-hand side is the derivative with respect to x of rad 1 plus x squared times y. And then the right-hand side just stays put for a second. Okay, we're focusing all our attention on that left-hand side. So you would have to use the product rule, right, to differentiate. Rad 1 plus x squared times y. So look, rad 1 plus x squared, say I leave it alone. And then the derivative of y with respect to x is dy dx. Okay, so far so good. And then I'm going to differentiate rad 1 plus x squared. So it would be 1 over 2 rad 1 plus x squared times another 2x by the chain rule, which is exactly what I have here. Those 2's cancel out. And then you leave the y alone, which, yes, we have here. So everything checks out. All right, then I know I'm free to proceed with a clear conscience in the following steps where I'm actually going to integrate and solve. If it doesn't work out, that the left-hand side really is the derivative with respect to x of mu of x times y, then you messed up somewhere, so go back and try to find your mistake. Okay, step 5. We will integrate now. So we have on the left-hand side, derivative with respect to x of rad 1 plus x squared times y. I'm integrating this with respect to x. And then that equals, same thing, integrate on the right-hand side, negative x squared minus x over radical 1 plus x squared dx. Okay, the left-hand side is easy squeezy because everything just cancels out and you're left with mu of x times y. So you just have radical 1 plus x squared times y. Okay, notice here we have a derivative with respect to x. We're integrating with respect to x. So those will all undo each other. Now, how to deal with the right-hand side? It's not for the faint of heart, my friends. If you'll recall, when you have an integral of the following form, it's time to use a good trig sub. If you've forgotten, I will link a video for you here from my Calculus 2 video lecture series playlist. Notice underneath the radical, I have 1 plus x squared. That signals that it's time to make the following substitution where you would let x equal a tan theta, which is 1 tan theta here. Ooh, do you remember doing this? I hope so. I certainly hope so. So then dx would be secant squared theta d theta. And then remember, I want to be able to rewrite everything in terms of theta in my integral. And that means that 1 plus x squared would be 1 plus tangent squared theta, which is secant squared theta. Okay, so let's see what we have here on the right-hand side once I make that substitution. We will have integral. In the denominator, I have radical 1 plus x squared. We just established that 1 plus x squared reduces to secant squared theta after I make that substitution. So here we go. In the numerator, remember, x is tangent theta. So we have negative tangent squared theta minus tangent theta. Okay, everything looks nice so far. And then don't forget dx is equal to secant squared theta d theta. So that gets tacked on right here, secant squared theta d theta. All right, let's focus our attention over here. Notice I have rad secant squared theta, which technically is the absolute value of secant theta, but remember we restrict theta to be in the appropriate quadrant so we don't have to worry about the absolute value. You don't have to write that out every time, just know that that's what's going on. So this will cancel because that's just secant theta to the first power now, and that's going to cancel with one of these secants, okay? Let's see, are things looking better? So we've got rad 1 plus x squared times y equals integral. This is negative tangent squared theta minus tangent theta times secant theta d theta. All right, let us go ahead and distribute this secant theta now, and then tackle each of the little integrals that result. I'm going to take the negative outside so it's not bothering us. And then we've got integral tangent squared theta secant theta d theta minus integral secant theta tangent theta d theta. All right, how to proceed? Well, I'll link another video here if you've forgotten some of the techniques on trig integrals. When tangent is raised to an even power and you have an odd exponent on secant theta, what you want to do is rewrite tangent squared as secant squared theta minus 1. And then I'm still going to leave everything else here. And I've got that secant theta d theta minus, now let's think, how would we tackle this? Secant theta tan theta d theta. You don't need to do a thing. That antiderivative you should know. You should memorize that one actually, okay? That one's just gonna be secant theta. I like to wait and integrate everything at the end because I don't want to take that antiderivative and then have this plus c hanging out the whole time and then throw in another constant. So I'm just going to rewrite it as is and integrate at the very last step everything all at the same time. Okay, so my solution looks really nice and clean. But I'm not worried about it. We can handle that. Okay, again, what was the point of rewriting tangent squared theta as secant squared theta minus 1? So we're going to distribute this secant theta now, and I'm going to have 3 little integrals. Oh, yes. So first one, negative integral secant cubed theta d theta plus integral, this is just secant theta to the first d theta, minus integral secant theta tan theta d theta. All right, what's the antiderivative of secant cubed theta? Do you know? Maybe you memorized it, probably not. The way to do this integral is by parts. And this one boomerangs. Oh my goodness, what do I mean by that? I'll link a video here where I show how to integrate it. Otherwise, if you want to just memorize it, or maybe your instructor will give it to you, it's a lengthy little integral to do within already a pretty lengthy problem. So if you're in my class, I would never put this on a test without giving it to you or making it a little bit more simple so you didn't have to do so many steps in the integration. Anyways, end of the day, if you could look it up, or maybe you also memorized a reduction formula, you will have the following. So negative antiderivative of secant cubed theta turns into 1/2 secant theta tan theta plus 1/2 natural log absolute value secant theta plus tan theta. So that's done. Let me scoot this over. Okay, so that's all antiderivative for secant cubed theta. Then I have plus antiderivative of secant theta, d theta, you should memorize this one already, natural log absolute value, secant theta plus tan theta. And then let's color code, we like it. So here's secant theta d theta, that becomes this guy. Then I have lastly minus antiderivative of secant theta tan theta. That one's the easiest of all. It's just secant theta, and then now I'm going to put my plus c. So here, that one took no work. We are done. And I just put one nice plus c. See how clean and classy? Okay, can we clean up a wee bit more? Of course we can. Notice here, I'll distribute the negative. Then I have negative 1/2 natural log secant theta plus tan theta, and this is positive 1 natural log absolute value secant theta plus tan theta. So these are actually like terms here. I can combine these two. You see that? And I can rewrite what I have as follows with one less term. Negative 1/2 secant theta tan theta plus 1/2 natural log absolute value secant theta plus tan theta minus secant theta plus c. All right, before you box things and think you're done, remember the original differential equation was all in terms of x, so we cannot leave it like this in terms of theta. How do we go back? Well, remember what that trig sub was that you used. We let x equal tangent of theta, right? So think of trig, that means x over 1 is tangent theta. You can draw yourself a nice little triangle. That's what I like to do. Here's theta. Tangent of theta is going to be opposite over adjacent, and then that means the hypotenuse is going to be rad 1 plus x squared. Okay, also, so I can rewrite these tangent thetas in terms of x. I'm also noticing I have secant thetas, right? So what's secant theta? Secant theta is hypotenuse over adjacent. So that means secant theta is going to be rad 1 plus x squared. Okay? We're almost done. Hang in there. So now, at long last, remember the left-hand side? How we had mu of x times y? Let's bring it back. Rad 1 plus x squared times y equals negative 1/2 secant theta. I'm looking here. Keep up. Secant theta is rad 1 plus x squared times tangent theta is x plus 1/2 natural log absolute value secant theta, which is rad 1 plus x squared plus x, minus secant theta, which is rad 1 plus x squared plus c. Everything checking out so far? Great. Last step, most fun of all, we're going to divide everything by rad 1 plus x squared so that we can isolate y. Okay, divide everything. You don't have to write this out. You probably can see by now, but let's just go step by step. And then we can box it after that last little move. Okay, so here we go. Y is equal to, oh look how nice these cancel, right? Bam, bam. I'm gonna write that as negative x over 2. Wouldn't that look so classy? Yes, negative x over 2. I would write this as plus 1 over 2 rad 1 plus x squared. Group that all together and then have natural log absolute value rad 1 plus x squared plus x minus, look at this term here, this is just going to be a 1, plus you need c over rad 1 plus x squared. You can't just call it a new constant because rad 1 plus x squared, that's a function, right, that varies as x varies. That will not all be expressed by just calling it some new constant, okay? So you can combine multiple constants and call them a new constant, but you can't take a constant times or divided by a variable function and then just call it some new constant. No. You'll lose all of what's going on over there with that term. Okay, now we can box it. All right, that example was not for the faint of heart. It basically reviewed so many Calculus 2 techniques. So if you have reviewing to do, check out, I have plenty of videos on how to integrate all of Calculus 2, but keep in mind that as a math student, you're not allowed to forget anything, okay? All right, good. Let's look at one more example for now, and then we'll do other examples in part 2 of this video. All right, we have x times y prime plus 2y is equal to e to the x plus natural log of x. I'm just kind of going to jump to the solution steps now. We know that this guy is going to be linear because we're talking about linear differential equations. So let's just confirm quickly. I'm going to isolate y prime. So remember our standard form is y prime plus p of x times y equals f of x, right? So just try to see if you can rewrite it in that form. So we've got y prime, I'm going to divide everything by x. Y prime plus, I'm going to write this as 2 over x times y. Try to keep that y to the first a little bit separate. And then this is equal to e to the x plus natural log of x over x. So yes, this is totally linear. Notice, here's my p of x. And then here is f of x. Bam. Now it's time to go find that integrating factor. So integrating factor mu of x is equal to e raised to the integral of p of x dx. So that's going to be e raised to the integral of, there's my p of x, 2 over x dx. Good. This is equal to e raised to the antiderivative of 2 over x is going to be 2 times natural log of absolute value of x. And then you can move the 2 to the exponent on x. So it's going to be absolute value of x squared. But you don't need the absolute value, right? Since x squared won't be negative. So you have e raised to the ln of x squared, which is just x squared. All right, step 3, we're going to multiply our standard form differential equation by the integrating factor. So I'm going to go here and multiply everything by x squared. So we have x squared y prime plus 2 over x times x squared times y equals x squared times e to the x plus ln of x over x. All right, so let's see here. We've got x squared y prime plus, this x cancels out here, so I just have 2xy, and that equals, more canceling fun here, that x is gone now in the denominator. So I have x times e to the x plus ln of x. All right, so far so good? Great. Now step 4, what you need to do is check that the left-hand side indeed is the derivative with respect to x of mu of x times y. Mu of x was x squared times y. Let's check. I've caught many a mistake at this step, so don't be lazy and skip it. So leave x squared alone and then take the derivative of y. Yep, that's y prime. Now take the derivative of x squared. There it is. And then leave y alone. Perfect product rule application. Love it. So everything's checking out. That means you're allowed to proceed to step 5. What is step 5? That's when we actually integrate and solve this guy. So we're going to integrate both sides now with respect to x. On the left-hand side, remember we had the derivative with respect to x of x squared times y. Don't forget to add your dx here. And then on the right-hand side, we're going to integrate x times e to the x plus ln of x. Integrate that now with respect to x. Okay. Left-hand side's my favorite. It just all reduces to x squared y. And then on the right-hand side, what we're going to do is distribute this x. And we're going to break it down into 2 integrals. So we've got integral x e to the x dx plus integral x ln of x dx. So we've got integral 1, integral 2. Do you recognize what technique we need to use to anti-differentiate both of these? I hope you do. It's by parts, right? Yes. So let's set it up. I'm just going to focus on integral 1. We'll do them separately, okay? So by parts time. Integral 1 is antiderivative of x e to the x dx. So remember, you pick your u and dv. And I want to let u equal x and dv be e to the x dx. Why? Because du is just going to be dx now. And v is e to the x. And remember, the only portion that I'm going to end up integrating is v du. So now I've made that a lot simpler since I just have dx and e to the x. Did you forget how to integrate by parts? I'll link a video here. This is just a linking frenzy today. Okay, so from here you have uv. That doesn't get integrated, right? So you have x e to the x minus v du. That does get integrated, so integral v du, e to the x dx. Oh, and then now it's no big deal, right? So you just have x e to the x minus e to the x plus, I'm going to call it C1 because I know I got another one of these integrals on deck, okay? That's on hold. Let's just put it in a gentle cloud. Very nice. Integral number 2, we have x ln of x dx. We're going to do by parts again. Now, in this very problem, we've already assigned the variables u and v to represent certain quantities. So please don't reuse them, all right? Put a hat on it, put a bar on it, do something else. So u bar and dv bar are my variables of choice for today. In this case, I need to let u bar be natural log of x, and dv bar is just going to be x dx, because then I can calculate v bar, right? 1/2 x squared. If I had done it the other way around, you don't know antiderivative of natural log of x. Actually, the way we find it is by doing integration by parts. So then now I can compute du bar. Derivative of natural log of x is just going to be 1/x dx. All right, things are looking nice. Now it's time to integrate. We have uv not integrated, so that's just going to be 1/2 x squared natural log of x minus integral of v du. Let's put that 1/2 outside. I love pulling those constants outside so I can really focus on the variables and what's going on. Integral 1/x times x squared dx. Notice I can cancel out an x. Good, good. So we've got 1/2 x squared natural log of x minus 1/2, you know the integral of x. It's just another 1/2 x squared plus, what should we call this constant? Yes, C2. Okay, and then last step to clean it up, we've got 1/2 x squared ln of x minus 1/4 x squared plus C2. Okay, we'll put this in another cute little cloud. All right, and then back to what the original problem was. Remember, we had mu of x times y, so x squared y equals, do you remember what was in that first little blue cloud? X e to the x minus e to the x. And then plus 1/2 x squared natural log of x minus 1/4 x squared, and then I'm going to put a plus c, where guess what, everybody? C is equal to C1 plus C2. Look how classy we are. And then last step, I want to divide everything by that integrating factor, x squared, so I can isolate y, right? That's the whole point, so we get a solution to the differential equation over x squared. And now we have, voila, y equals e to the x over x minus e to the x over x squared plus, ooh, this is nice, just 1/2 ln of x minus 1/4 plus c over x squared, which you leave, right? Good. Don't do anything wild. Don't pull some illegal math maneuver. The math police will come for you. Okay, that concludes part 1. Stay tuned for part 2. We'll solve some more. We'll throw in an initial condition. We'll make it spicy, but work on that. Perhaps you have some integration techniques to review. It's all good. Stay tuned. Be sure to give this video a thumbs up if it was helpful, if you enjoyed it, and share it with your classmates, friends, whoever else might find it helpful.